Now I want to actually look at the Fourier coefficients and see where those integral formulas came from. One of the things that we'll use in our derivations is the 5 integrals we have here. So let's assume m and n are integers. Then we're going to use the fact that the integral of sine mx or cosine mx from minus pi to pi would give us 0. If we integrate from minus pi to pi a product of two sine functions, sine of mx and sine of nx, or cosine of mx and cosine of nx, these will always be 0 if m and n are not equal. But if they are equal, in which case we're integrating either a sine squared function or a cosine squared function, then we get pi. And then finally, the integral from minus pi to pi of sine mx times cosine of nx is always going to be 0, even if the m and n values are the same. So I'll scroll back up to those as we need them. But the underlying assumption we're going to make here is that it's possible to write our 2 pi periodic function f of x in the form of a Fourier series. So let's assume that's true and then figure out how we would have to define those coefficients in order for those two sides to be equal. So the first thing I'd like to look at is where we get the formula for the additive constant a sub 0. So I'm going to take the equation in the green box and let's integrate both sides. So let's look at how we come up with this. So if I integrate both sides of that equation from minus pi to pi, then this still should have that those are equal. So we're going to have then that the integral from minus pi to pi of f of x is equal to the integral from minus pi to pi of a sub 0 plus the integral from minus pi to pi of the sum of ak cosine kx, and then finally plus the integral from minus pi to pi of the sum of bk times sine kx. Now, a couple things we can do here. First of all, notice that this first integral is just the integral of a constant, so I can just take the value of that constant times the length of the interval, which is 2 pi here. And then, much like we saw when we were integrating power series, I'm going to treat the integral of a sum as the sum of the integrals of the terms. So bringing this integral inside, the other thing I want to focus on is the fact that these are integrals with respect to x. So when I bring that inside of the sum, I also can bring the coefficient a sub k out of the integral, so it still needs to stay within the sum. So to be clear, I could just write the integral of ak cosine kx here. However, the a sub k does not need to be inside of the integral. And so this is one way I could rewrite that middle term, and then I can do a very similar thing for the last term, expressing this as the sum of b sub k times the integral from minus pi to pi of sine of kx. Now, for those integrals, in particular, looking at, we're going to think about for a fixed value of k, integrating this cosine of kx, where kx is 1, 2, 3, etc. Well, if we look back at our formulas, notice that that comes back to number 2. And that's saying for each of our possible values of k, this is going to evaluate to 0. So what would happen is we would be summing there 0 plus 0 plus 0, so that whole middle term is going to get wiped out. Likewise, if I consider the sine of kx integral from minus pi to pi, that is our first formula up here, and we said for any integer value k that would be 0. So we can now wipe that out. And likewise, every single term now, b sub k, is multiplied by 0, so that entire sum is 0. And let's look what we have left. So we have on the left-hand side the integral from minus pi to pi of f of x. And on the right-hand side, we have a sub 0 times 2 pi, and everything else vanished. So if I were to divide both sides by 2 pi, this would leave me with the formula a sub 0 would have to be 1 over 2 pi times the integral from minus pi to pi of f of x. And that's, of course, exactly how we defined it when we wrote down the Fourier series, but now we see where that comes from. So how do we come up with either a sub k or b sub k? I'm going to go through just one of them because there'll be a symmetric argument about cosine versus sine. And the other thing I want to do here is, instead of trying to find a formula for a sub k or b sub k, I'm just going to pick out a very specific coefficient. For instance, let's look at a sub 3. And it will be easy to see how I could use what we do here to derive either b sub 3, or then change that 3 to any other positive whole number. So I'm going to go back to the original assumption of this green boxed equation. And what I'm going to do first here is I'm going to multiply everything in this equation by the same thing, so it still holds equal. But what I'm going to multiply by is cosine of 3x. So if we do that, the green equation, I multiply everything by cosine of 3x, then that's going to tell me that f of x times cosine of 3x is equal to a naught times cosine 3x plus the sum from k equals 1 to infinity of ak cosine kx times cosine 3x plus the sum from k equals 1 to infinity of b sub k sine kx times cosine of 3x. So the reason I'm multiplying by cosine of 3x is I know that I'm hoping to see how a sub 3 relates to an integral involving cosine of 3x. So now these two sides have to be equal. And then again, if I integrate both sides from minus pi to pi, the result should be equal as well. So that tells me here that the integral from minus pi to pi of f of x times cosine 3x is equal to the integral of that first term, which I'm going to factor out a sub 0, plus the integral of the middle term. Now I'm going to skip a step here because we already talked about it in the previous line. When I write the integral of the sum, I'm going to instead bring the integral inside of that summation, and likewise recognize that I can bring a sub k not outside of the sum, but outside of the integral that's a dx integral. That will leave a sub k multiplied by the integral from minus pi to pi of cosine kx times cosine 3x. And then finally, we will have the same kind of thing with this last term. This will now be the sum of b sub k times the integral from minus pi to pi of sine, sine kx times cosine 3x. Okay, so now let's think about what we can say here. Again, if I focus on these one at a time, I can see here I have the integral of cosine of 3x. That comes from our second formula, where m is 3. And I know that that's going to go to 0. And consequently, that's going to make a sub 0 vanish. Let me jump to the third term here and focus on the fact that this involves integrals of the form sine kx times cosine 3x. If we look back, that is formula 5. We said that no matter what the k value in this case would be, that's always going to be 0. And so we can, I want to do a different color there. We can wipe that out. So that's from formula 5. So every b sub k is now multiplied by 0. And so that's going to wipe out that entire sum. We have to just be a little bit careful with this last part here. So focusing on this part, this is going to relate to, when we have cosine times cosine, our fourth formula, And notice here we see that you either get 0 or you get pi. And you only get pi when you are multiplying two of the exact same cosine functions together. So if I were to write that out, that's going to give me a1 times the integral of cosine 1x times cosine 3x. Well, according to our formula, that's 0. Plus a2 times the integral of cosine 2x times cosine 3x. That's going to be 0. Plus a3. Now when I get to a3, the integral of cosine 3x times cosine 3x, according to formula 4, in that instance, the integral is pi. And then when I get to a4, I have cosine 4x times cosine 3x. And anything after this is likewise going to be multiplied by 0 because the argument of the cosine function does not match. This means that what we're actually finding here is that the integral that we started with, which was the integral from minus pi to pi of f of x times cosine 3x, is equal to the only thing that's not 0 on the right side, which is pi times a3. And if I wanted to then isolate a3, I end up with 1 over pi times the integral from minus pi to pi of f of x cosine 3x. And of course, this is, again, how we defined this before. So now we can see what might have been originally confusing, why we have a 1 over 2 pi in front of a sub 0, whereas we have a 1 over pi for all of our other integral formulas. The other thing to note here is that if we wanted to derive a sub k for a different value of k, let's say 10, well, the only difference is I would have started by multiplying by cosine of 10x. And then finally, if I wanted to derive the formula for any of my b sub k coefficients, the only difference is that I would first multiply by the appropriate sine function to get to the final formula.